Welcome to Ask and Learn.
So we want to produce the graph of f of x is equal to x to the fifth minus x to the fourth minus x cubed plus 28x squared minus x. And in particularly, we want to use the graphs of f prime and f double prime to estimate our intervals where the function is decreasing and increasing, any extreme values, intervals of concavity, and inflection points. All right. So just to kind of save time, so in this first one here, I went ahead and already plotted the graphs of f prime, and f double prime. And remember, to find these derivatives, we would just go ahead and use power rule. Now, in this first graph over here, when I just plug this into my graphing calculator to start, you can see that the viewing rectangle that it gives isn't all that good. So now, if we use a little bit of calculus, we can figure out a better viewing rectangle for it. So when I take the first derivative, since we're interested in where the function is increasing and decreasing, all we really care about is where all the intercepts are. So I zoomed out far enough so I can see all of the intercepts. And since this is a fourth degree polynomial, and it has 1, 2, 3, 4 intercepts here, we know this is all we really care about. So what we can now do is say that points that may be of interest are going to be these intercepts, because those are going to be our possible critical values. And we can see that we can estimate our intervals of increasing and decreasing by just looking for where this is positive and where it's negative. So we know f prime of x is going to be strictly larger than 0 on, so to the left of negative 1.5, so negative infinity to negative 1.5. And then after 0.036 to 2.623, so 2 point, actually let me go ahead and write this a little bit over here, 2.62, first 0.036 to 2.623. And then our last interval where it will be larger will be 2.841 to infinity. I'm going to go ahead and scoot this up a little bit. All right. Now we can go ahead and find where it's less than 0, which would just be the rest of our intervals. So f prime of x is strictly less than 0. So between negative 1.5 and 0.036, it'll be negative. So negative 1.5 to 0.036, as well as 2.623 to 2.841. All right. So we can see that all of these have a change in concavity, in a change in its derivative. So to the left of negative 1.5, it's positive. To the right, it's negative. So that means at 1.5, there's going to be if I increase into something and then decrease after by the first derivative test, that tells me it's going to be a max. At 0.036, we're going to have a min that occurs. At 2.683, we're increasing into the point and then decreasing after. So this is going to be a max. And then the last one is going to be a min. All right. So we at least know when we're looking at our viewing rectangle, we should at least go from negative 1.5 to 2.84 at a minimum, because these have important x values for us. Now, let's go ahead and look at f double prime. So here, this is a third degree polynomial, and here we have our 3 intercepts. So we at least know this is as wide as we need to do it. And just like before, we're going to look for where it's larger than 0, less than 0, so we can find concave up and concave down. And maybe I should say up here, but remember f double prime, or f prime larger than 0 is a increasing interval, and f prime less than 0 is a decreasing interval. Okay. Now let's go ahead and figure out where f double prime is less than 0 and greater than 0. So when f double prime is strictly larger than 0, this tells us we're going to be concave up. So our first interval of that is going to be from negative 0.888 to 1.153. And then we'll be positive again, 2.735 to infinity. Now we can go ahead and find where our function is concave down, or when f double prime is strictly less than 0. And that will just be our remaining intervals. So negative infinity to negative 0.888. And we'll also have 1.153 to 2.735. Right. Now let's go ahead and see what's going on with these points. So we're changing concavity at each of them. So to the left of x is equal to negative 0.888, it's down and then up. So this is an inflection point. Likewise for 1.153, it goes from up to down, and then 2.735, it goes from down to up. So we know all three of these will be points of inflection. All right, so now we have some ideas of x values that we need to include into our graph at a minimum. So I went ahead and plugged these values into a graph here, or into the equation f of x. And so the reason I chose my interval for the x values to range from negative 3 to 3 is my smallest value for my x's is negative 1.5. And just to make sure we get the rest of our end behavior, if we were to just have negative 1.5, which would be this maximum right here, we wouldn't include this 0. So when you would first graph it the first time, you would see that you're still missing some end behavior. So then you would just go ahead and go a little bit further so we can get our other x-intercept in there. And I chose the interval 3 since our largest value on x was about 2.7. And when we would graph that, we would see it's going up and still increasing. So I would just know the end behavior would be going to infinity. So that's why I just chose 3 and didn't really have to go much further than that. And then likewise for the y values that I chose, well, my smallest value was this one here, so about negative 0.03. So I just chose negative 1. And for my largest value, I went ahead and chose 50 or 60 because my largest output that I get for these important points is at 56. About. Okay, so that's why I chose my viewing window. But you might notice that at our smallest value here, it says we should have something going on. But if we look at that little interval right here, just looking at it on this graph, it still doesn't look very good. So if we go ahead and blow that up, we can actually see that around that point, we do actually have a local minimum. So this is how you would go about solving these kinds of problems to get a good viewing window of your graph. You would find your points where you have maxes, mins, or just critical values, as well as possible points of inflection, and then play around with your new window until you get everything in there. And then if you have any kind of weird behavior, kind of like we did around x is equal to 0, you can just blow those up to go ahead and give a better idea of what it should look like.